So first of all, let me thank the organizers for giving me the opportunity to speak today. So this work was done in the BC Center in Trento, collaboration with Stéphanie Mater, Gianluca Rastelli and Jacopo Carusotto. So the main idea behind our work is to consider coherent light entering in a nonlinear medium, which we already seen a lot of times during this week, and to consider a regime which is very strongly correlated. So the idea is to change the nonlinearity of the medium very slowly in space, so start from a very low nonlinearity up to a very strong nonlinearity, and convert coherent radiation adiabatically into strongly correlated radiation, in particular in the Tonks-Girardeau regime, so exhibiting anti-bunching and Friedel oscillations in the pair correlation functions. So the way to describe this will be in this TZ mapping idea, and the idea is to quantize the field with the role of time and Z exchanged. So the platform we are studying is superconducting circuits, where the important component is a Josephson junction, which gives the nonlinearity to the medium. And this is done because the relation between the current through the junction and the phase across it is nonlinear. So we are studying propagating waveguide, which is similar, so to say, to like a coaxial cable, but where the inductance now it's a Josephson junction, so it's nonlinear and has a nonlinearity which is important at the level of single photons, so exhibit quantum behavior. This has already been used, for example, in much more complicated configurations as traveling wave parametric amplifiers, which are used to amplify a very weak signal by using a pump and exploit 3-wave or 4-wave mixing. So actually this much more simple model can actually model also much more complicated configurations, so that they just fall back into this one. They just have more knobs, let's say, experimentally. So the way we set up the description is first we figure out Lagrangian, which gives the equation of motion of the propagation of our field inside the waveguide. And this has kinetic terms and then nonlinear terms due to the Josephson junction. So the first approximation we do is a slow envelope approximation. So we say we enter with a coherent field with some frequency omega naught and some wave vector k naught, and we just expand around that. Then we assume we do some rotating wave approximation to treat the nonlinear term arising from this cosine, and we assume that the intensity is weak with respect to one quantum of flux. This allows us to write an effective equation, which can be summarized in this way. So this f of k omega contains all the linear part of the propagation. So the zeros of this function are the dispersion relation. And then around this point, we can say that this is not zero, but it's equal to a very small function of the intensity of the field, which we treat as a perturbation. So we can actually move in this curve. So we change the frequency a little bit, which corresponds to changing the wave vector, corresponding to the group velocity and the dispersion relation, plus a term which depends on the strength of the interaction. This gives the nonlinear part of the evolution. And one ends up with an equation after, let's say, subtracting the group velocity by adding a field, a phase to the field. One ends up with an equation, as we have already seen, which is exactly a nonlinear Schrödinger equation, so a mass term, which is given by the curvature of the dispersion relation, and a nonlinearity, which is given by the Josephson junction. Now we want to enter a strongly correlated regime. So we wonder so this is a mean field theory. We wonder what is the quantum theory that can describe a regime, a much more correlated regime. So first of all, we have the Lagrangian of this Schrödinger equation, which is not completely determined by the evolution, because we can always multiply it by a constant. This does not change the classical equation of motions, but it will change the commutation relation when we quantize the theory. And then we have the physical Lagrangian we started with. So what we can do is actually to compute the energy of a plane wave in the two pictures and to make them equal. And this will give us the value of this n in front here. And this way we have completely determined our Lagrangian in this nonlinear Schrödinger picture. So since we have changed the role of t and z, we can just change coordinates just to have the right dimensions. So now we have a Lagrangian, which is the Lagrangian of the linear Schrödinger equation. We can compute its conjugate momentum and then impose canonical commutation relation. These are equal tau commutation relation, which are actually equal z commutation relation, which is not what you would usually do with a field, but since we are in this TZ mapping, this is how we get an effective quantum theory. And this gives us the strength of the interaction, which is dependent on this coefficient here in front of the bosonic field. And now we arrive to an equation which is exactly the Lieb-Liniger model that has already been discussed. So we can look at these parameters as a function of the circuit element and get their behavior. Tonks-Girardeau gas has already been explained, so I'll be very fast. This can be solved with a Bethe ansatz. In particular, if you go to zero interaction, you have this coherent light, which is what enters the medium. And if the interaction goes to infinity, you have this anti-bunching and these Friedel oscillations, which are a many-body effect. So the transition is governed by this dimensionless parameter. Of course, the interaction is on the numerator, so if we increase the interaction, we have a more interacting gas, but the density is at the denominator. So if we decrease the intensity of our field, we actually have a much more interacting system. So we can actually plug in some reasonable numbers that are used usually for this kind of systems, and we see that gamma, for example, is unity. So the idea is that in these systems we can actually achieve this very strong interacting regime. So now we want to change the nonlinearity in space very slowly, so starting from 0 and going to a very, very high, which corresponds to changing in time the interaction of a one-dimensional gas. But doing this adiabatically has drawback that the excitation spectrum is gapless. So there's no adiabatic theorem that guarantees to you that if you go slow enough, you will convert a ground state to another ground state. So we set up some numerical simulations. We can discretize the Hamiltonian with a very, very small spacing L, which gets mapped into a Bose-Hubbard Hamiltonian that can then be, so its time evolution can be simulating using a tensor network. So we use the transition invariant MPS, so to directly go into the thermodynamic limit, which would correspond in the TZ mapping to a stationary state. So first result is, so first of all, the first result is actually analytical. So if we change the inductance in our waveguide, so the mass will go as the inductance to the -1, whereas the interaction will scale proportionally. So if we look at the equation of motion, we can rescale time as the inverse of the inductance. This means that if you take a certain waveguide and to generate a Tonks-Girardeau you need some given time. If you just double the inductance, you will need half that time. Then we can look at some evolutions, and we actually see that if we are very slow, so you see the green dots over here, we can actually convert this initial coherent radiation into a field that actually displays these oscillations that are typical of the Tonks-Girardeau. If we are instead faster, what will happen is what you see here in blue. So you will create some anti-bunching, which is a much more, much more energetic, not to have anti-bunching instead of the Friedel oscillations. And then you will create a peak in the pair correlation function, which will then spread with twice the velocity of sound in Z. So then one can wonder what happens if one changes the initial intensity of the laser field. So actually one changes the density in our Bose-Hubbard Hamiltonian. One sees that there's some universal scaling. So here you see the time it takes to get the ramp. So here you can imagine this is very fast ramp, this is a very slow ramp. And on the y-axis is the excitation energy. Both are normalized to the ground state energy. So this is the ground state energy of a Fermi gas. And you see that there's some universal behavior. So we can say that time times the ground state energy is more or less a constant. And this means that the time scales as rho to the minus 2, meaning that if I have a much more intense flux at the beginning, I will have a much faster dynamic, so a much faster adiabatic dynamic. This we can also see with plugging in some parameters for a waveguide, that we take the same exact waveguide, we just change the photon flux at the beginning, we get so some very much more excited state to a much less excited state. Then we can also look at first order correlations in a system. So if we do a very, very fast ramp, the system retains memory of the initial coherent state that had a flat pair correlation function. So what you see here in red is that so the correlations start to decay and then they are flat because there is still memory of the initial state. If we do still a fast ramp but a bit slower, so correlations have time to spread, there is an exponential decay of the correlation. This memory effect was, for example, already seen in cold atoms, as we already said during this conference. And so this one in blue, see that it decays exponentially, and then at some point it does not anymore, and this is due to both still memory effect and some approximation due to MPS, which affect the long distance correlations that are not that well captured by an MPS ansatz. If we do much slower ramp, what we see is that so we can convert our state to a Tonks-Girardeau state, and we end up in this algebraic decay of correlation, so this 1 over x to the 1/2. So the curve in orange is the Tonks-Girardeau prediction, and the curve in blue is the result after evolution, so starting from a coherent state and getting with a time evolution by changing the ramp. And you see that it has this algebraic decay of correlations. So let me conclude. So we saw that we can build an effective quantum theory for the propagation of a photon field in a superconducting waveguide. And it is also possible to use this to adiabatically generate Tonks-Girardeau gas of photons, which displays fermionic properties. What we saw is that if you want a faster dynamic, you should try to have highest possible inductance and the highest possible intensity at the beginning, with the drawback that if you increase the intensity, you have a less interacting gas. So you must find a compromise between the two. Then future developments would be to investigate the role of losses, which are assumed to change the physics when you go into the strongly correlated phase, and to look at way to engineer the dispersion, which is something that people already do in these superconducting circuits, to actually increase the interaction strength and decrease the mass. Because if you decrease the mass, the adiabatic evolution will be much, much faster. And with this, I thank you for your attention.